So in this video, I'd like to ask a question regarding delayed reaction between two charged particles. So what I mean by that is if you have two charged particles, let's say they're both equally charged positive particles, um, theoretically, as I understand, since the speed of light is finite, if one particle moves towards the other, there will be a time delay before this particle will sort of sense that this particle began to move. So that's my basic understanding. And in this case, like in this example, it's like they're separated by 1 unit of measure. But let's say theoretically, if they were 1 meter apart, that time delay would be about 3.3 nanoseconds. And if they're 1 foot apart, it will be about 1 nanosecond. Theoretically, that's like how long the impulse from one charged particle would take to reach the other charged particle. So the question I would like to ask is in regards to an energy discrepancy that can arise if you take into account the delay of the electrostatic impulse between the two particles. And I will try to demonstrate that discrepancy with two scenarios. The first being where the two charged particles are moved towards each other simultaneously, where you take into account the delay of the electrostatic fields. And in the second scenario, I will just move one particle towards the other. And in that case, I will not take into account any delay of electrostatic fields. So in the first scenario, I will move each particle 0.1 units towards the other simultaneously. And I'm trying to demonstrate that here with these cutouts being moved magnetically towards each other simultaneously. And the result is that once they're moved, they're now a distance of 0.8 units of measure apart. But each particle only traveled basically from 1 to 0.9, assuming that the movement was completed before the two particles exchanged electrostatic impulses caused by their movement. So to try to calculate the energy used to move them together, I use this equation. It's basically a simplified version of Coulomb's law. And I know Coulomb's law has like constants and the charges included, but I'm just using a simplified inverse square equation here just to simplify these calculations. So I basically calculate the integral of a single particle moving from position 1 to position 0.9, and then I multiply that result by 2 to get the work used on both particles. So the result that I got is 1/9 multiplied by 2, which results in a continuous or like a repeating decimal of 0.22. So basically 0.22 continuous units of energy were used to move the two particles closer to each other. Now in the second scenario, I will move just one particle 0.2 units of measure closer to the other. And again, I'm going to demonstrate that by using these cutouts. So one will stand still and the other will move 0.2 units. And the result again will be, in this case, the particles will end up being 0.8 units apart. And so the equation that I'm going to use to calculate the work done will be slightly different. So I'm going to just basically use the integral of 1 to 0.8 for a single particle. And again, after I do these calculations, I end up with a result of 1/4 or 0.25 units of energy used. So again, that's like a different result from the other scenario where you move the two particles together simultaneously. So here I'm comparing the two theoretical equations from the two scenarios, and the equation from the first scenario is on the bottom. And I understand that this result is sort of exaggerated because in reality there would not be such a large delay in reaction, like the time delay would not be that great between the two particles. But I'm just saying that if it would exist on like this kind of large scale, would it also exist on a even more minute scale? You know, it just seems that even on a minute scale there would still be this slight energy discrepancy that could arise due to this delayed action between charged particles. So that's just the question that I had. And also I'd like to add that I think it seems that this would also work in reverse, meaning like if you were to bring two equally charged particles really close to each other and release them, they would repel against each other, but they would be repelling against a slightly delayed electrostatic field. So, I mean, I think this would also work in reverse, where as the particles repel from each other, there would still be a kind of energy discrepancy of like the kinetic energy that they would attain, because they'll be sort of, deflecting against a delayed electrostatic field. So that's the basic question that I've been curious about. It seems quite simple, and I would say that I've seen more complex things being discussed in quantum mechanics, such as entangled particles and those sorts of things. And maybe this question is kind of well known regarding these two charged particles and delayed action, but I feel like I have never really seen it. So, I mean, if anybody is familiar with it, it would be interesting to know about. If not, it seems like an interesting thing to kind of discuss and theorize about. And one more thing I would add is that when you have two like charges being pushed towards each other, I understand that they would create counteracting magnetic fields. So that's like another detail, but I'm not sure if that would affect this question of the energy discrepancy. So that was just something that I thought I would throw in there. But also, I did ask a similar question on StackExchange, though kind of an electromagnet version of the question, where two electromagnets are repelling against each other, and if you shut off one electromagnet, will the other magnet repel off of the delayed electromagnetic field of the shut-off magnet? And I did get an answer, and someone said that theoretically it should generate an impulse. So I thought that was kind of interesting. So I'll put a link in the description, and maybe that's like an interesting thing to discuss, So thank you for watching.